Welcome in. Today we're diving into David McKay's classic text, Information Theory, Inference, and Learning Algorithms. We're going to track down this one single powerful idea, a kind of golden thread that weaves through everything from sending clear pictures from deep space to cracking wartime codes, and even to the very logic that makes artificial intelligence work.
So let's jump right in with a classic puzzle from the book itself. Now, this isn't just some fun brain teaser, it's really a game all about information. And what it's really asking is this: how do you strategically and systematically get rid of what you don't know?
So right at the beginning, we are completely in the dark. Any one of these 24 possibilities could be the right answer. And our goal, well, it's not just about finding the one different ball. It's about how we design our little experiments, the weighings, to kill off wrong answers in the most efficient way possible. And here's where we get to the core idea. The absolute best strategy is one that makes each outcome, left side tips, right side tips, or they stay balanced, equally likely. Now, why is that so powerful? Because it means no matter what happens, you're guaranteed to gain the most information possible. You're just slicing away the biggest possible piece of I don't know every single time. So get this, we've basically just defined information. It's not some vague idea, it's something we can measure. It's the reduction of uncertainty. In that little game, information was the currency. So the next logical question is, can we actually put a number on it? Can we count this stuff?
All right, let's get into our first big pillar here and see how this all connects. That puzzle leads us straight to the groundbreaking work of Claude Shannon and the whole mathematical framework for measuring information. Okay, don't get scared off by the word entropy or the formulas. Just think of it like this. It's basically a measure of surprise. If I told you the next letter in this sentence was going to be a Z, you'd be pretty surprised, right? That's a high information event. But if I told you the next letter was an E, well, that's not surprising at all. It's super common. That's a very low information event. And this table, with data straight from the book, just nails this point home. I mean, just look at the probabilities for letters in English. The fact that E is so common means when you see one, it doesn't tell you much. It carries very little information. But look down at Q, J, or Z. They're incredibly rare. So when one of them shows up, wow, it's packed with information. It resolves a ton of uncertainty. Okay, so we can measure information. That's cool. But what do we actually do with it? How do we use it to reason about the world around us? How do we update what we think we know when new data, new information starts rolling in? You've probably seen this equation before. This is the famous Bayes' rule. But McKay wants us to see it not as some dusty old formula in a textbook, but as this living, breathing engine for learning. It is the mathematical recipe for how a rational mind ought to change when it sees new evidence. It's this really elegant, beautiful cycle. You start with a hunch, a hypothesis, that's your prior. Then you go out and see some evidence. You weigh that evidence using what's called the likelihood. And then you come out the other side with a new, refined, updated hypothesis, your posterior belief. And that posterior, well, that just becomes your new starting point, your new prior for the next time you see something new. That right there is the process of learning put into math.
So at the end of the day, it's all about this journey. This engine takes your starting guess, your prior, and it combines it with real-world data to give you a more refined conclusion, the posterior. It's a principled way to move from I have no idea to I'm pretty sure, and the fuel for that whole journey is information. Okay, so we've got the pieces. We can measure information, and we have an engine that uses it for reasoning. Now we get to the big reveal. This is the book's central unifying idea, the golden thread that ties this all together in a way that is just wow.
Now, stick with me here, because on the surface, these two things look like they live on different planets. You've got data compression, that's for tech folks, trying to shrink files down to save space. And then you have Bayesian inference. That's for scientists and philosophers thinking about belief and evidence. Totally different fields, right? Wrong. McKay shows us they are fundamentally the exact same job.
Just let that sink in for a second. To squish a file, you have to find all its patterns and predictable parts, right? You're basically building a model of whatever process created that data. Well, guess what? That is exactly what inference is. It's finding a model to explain where the data came from. They're the same thing. Learning is compression. Incredible.
Okay, so this is a beautiful idea, for sure. But does it actually do anything in the real world? Oh, yeah. Let's take a look at what this wild fusion of ideas has actually built. You know those amazing pictures of Jupiter we got from the Galileo space probe? The signal from out there was unbelievably faint, like trying to hear a whisper in a hurricane. But error-correcting codes, which are a direct application of information theory, allowed engineers to perfectly piece the data back together. It's literally building a model of the noise and static so you can perfectly subtract it out and see the picture underneath. And this way of thinking isn't new, not by a long shot. Back in World War II, the codebreakers at Bletchley Park were using a raw form of this. They'd look at two coded messages and basically ask, what are the odds, what's the likelihood, that these were made with the same settings on the Enigma machine? It allowed them to find these tiny statistical patterns that were totally invisible to the naked eye, and it helped change the course of the war.
Now, fast forward to today, and this is the absolute core of the AI revolution. When you see an AI that can spot a cat in a photo, what's it actually doing? It's not magic. It's building a super complex statistical model of catness by looking at millions of examples. It's doing inference to find patterns. It is, quite literally, finding the most efficient, compressed way to describe what makes a cat a cat.
The book also talks about this really cool idea called a digital fountain. I love this. Instead of sending a file like, here's piece 1, here's piece 2, imagine you just turn on a hose that sprays out endless, unique droplets of data. The amazing part is, your computer just needs to catch enough of these droplets, any of them, it doesn't matter which ones are in what order, to perfectly rebuild the whole file. It's an incredibly robust idea, and it's all built on these principles.
And this brings us to the end, and to maybe the most important, almost philosophical point in the whole book. What he's saying is, you can't learn from a totally blank slate. You have to start somewhere. You need a prior. You need an assumption. And the beauty of this entire framework is that it doesn't try to hide that. It makes you put your assumptions right there on the table for everyone to see. And then it gives you this powerful, logical engine for updating those assumptions when you actually see the world. It's simple, it's profound, and it might just be the architecture of learning itself.